Hello everyone, it's Benny, and welcome back to Occlusion Culling. Last time, we talked about occlusion queries, and we showed it was an amazing way to do occlusion culling, except for one small but extremely painful issue: the CPU-GPU sync. It's a huge pain for everything. It is the Achilles heel of the technique. So, what if we could get rid of it? What if we could do occlusion culling either entirely GPU side or entirely CPU side, and then not have to deal with that? In theory, it could be the ultimate occlusion culling technique. In theory. So today, we're going to look at software occlusion culling, specifically the masked variant, but we'll get to that in a second. Right now, we're just going to talk about what it takes to do everything CPU side and see if we can get the ultimate occlusion culling technique. So, in the world of software occlusion culling, here's the story so far. The idea, like I said, occlusion queries, except do everything CPU side. So you're still going to have a depth buffer, except the depth buffer is going to be drawn by the CPU. You are still going to be testing things against this depth buffer, except all on the CPU. And the benefit of this is, assuming all of that can be done easily, really fast and everything, I can determine right then and there, oh hey, this object's occluded. I don't even need to bother the GPU with this object. I don't need to tell it to draw it. I don't need to submit it. Doesn't matter. The GPU will only receive precisely what it needs to work with, because the CPU is just culling everything before the GPU even sees it, which has some really cool potential. But the big problem is the CPU rendering is slow. Seems pretty obvious, right? I mean, if the CPU rendering was fast, we wouldn't have GPUs to begin with. So, how can we overcome this? Can we overcome this? That's what Intel famously asked in 2013. They actually did a whole bunch of research on it. They have a whole research paper. They have a demo, looks a little bit like this. They want to see, can software occlusion culling be practically done? And the answer is yes! Sort of. Of course there's limitations. The big drawback is it's fast, but not quite fast enough. They pulled out a huge number of optimization sorcery, and it still required all 4 threads firing, and a special occlusion mesh, and a lot of other tricks to run well. But it's plausible given those conditions, but they're not... It's difficult to make that work for a real game. And the biggest thing is just the depth buffer size. It's 8 megabytes for a 1080p depth buffer, which is a huge amount of data. That's bigger than most CPU caches, or if it does fit in the cache, it's going to be crowding the whole thing. So you're going to be fetching from RAM a lot, which is a huge bottleneck. Fetching from RAM is very slow, especially in high-performance operations like rendering. And also, 8 megabytes is just a lot of data to begin with, even if that all did fit into the cache somehow, which, by the way, they found a way to essentially get this mostly fitting in the cache for most of the rasterization. That was one of their big tricks. Even if you do get it fitting all in the cache, that's just a huge amount of data to be operating on every single frame, 60 frames a second, with lots of logic and all the rasterizing and rendering logic. So it blows the cache for all intents and purposes. It's a huge amount of data for all intents and purposes. That's really the limiting factor. If you could somehow get the depth buffer to be smaller, well, then you're talking. You already have this huge bag of optimization tricks. They work very well. It's just a little bit smaller. Whole thing becomes practical all of a sudden. So can you make it smaller? No. You can't make it smaller, not in the intuitive way anyways, because of fill convention issues. Let's say I was drawing, in my for example, depth buffer, let's say I'm drawing this pillar. Right? If this is an occluder, then ideally I want to err on the edge of caution. I want to make this take up more pixels than necessary if I have it like an edge case. Yeah, if there's an edge case, it should take up more pixels than necessary. Because I don't want it to say, if it takes up less pixels than necessary, I don't want it to say it's not occluding something when it actually is. But the thing is, if I want to draw an occludee, so I want to test something for occlusion, I want to do exactly the opposite. I want to take up less pixels than necessary, given an edge case, because I don't want to accidentally say, hey, this thing is not occluded, or excuse me, backwards. I don't want to accidentally say it is occluded when it's actually not, because that will cause invisible objects to suddenly just disappear from frame. As we already talked about that in earlier videos, that's just not good all around. So you can't easily lower the resolution. It's technically not unsolvable, but it's very difficult and you don't want to deal with it. You could try saying, hey, let's use 16-bit floats, but that only cuts the size in half. It's still slow, it's still big, and also working with the 16-bit floats will slow down your performance a bit, so it's not a good idea. So this is a state. This is where software occlusion culling by itself is. It looks like it could be possible. It looks like there might be a good way to do it if you get the depth buffer smaller. But how can you get it smaller? This is where the mask comes into play. So, what is this mask? What is the magical data structure that can reduce the size of our depth buffer to a completely reasonable size? Well, the idea is to stop thinking so much in terms of this is what the depth buffer looks like, how do I make it smaller? And start thinking more in terms of compressed textures. How could we apply some form of texture compression to the depth buffer? Well, an easy form of texture compression, if you don't care too much about certain qualities, is just representing your image as a bit mask. So 0 is where nothing is, and 1 is where whatever you want to draw is. So I want to draw a triangle in a bit mask. This is what it might look like. I just flip 1 wherever whatever I want the triangle to be is. And yeah, this is a really tiny way to draw images. But you can probably already see an issue with this. This can't work for depth buffer by itself because it has no depth information. Go figure. But that's actually okay, because what we can do is we can sort of artificially add in depth information to this already really tiny format. So wherever there's a 0, we'll have a single float for that. One float for saying, okay, everywhere that's 0 is considered to have this depth. And we'll have another float that says, okay, everywhere that's 1 is considered to have this depth. So yeah, this can have depth information for a given image. It's a really tiny way to store depth information. The biggest issue, though, is this isn't really precise. This can't give me the exact precise depth at every single pixel. But that's actually okay, because we don't need a precise depth for every single pixel. Really, we just need sort of a general idea. We need to be close enough to be able to do occlusion tests. And if that's not entirely precise, we're okay with that, given some condition. But for all intents and purposes, we're okay with that. So this is practical. This is a way we could store a compressed depth buffer. It will be 12 bytes per tile. We're assuming 8x4 tiles, which means for a 1080p depth buffer, 777 kilobytes. Way down from 8 megabytes. We're down a whole order of magnitude. 777 kilobytes, that can easily fit in the cache of just about any CPU made in the last 10 years. And it's well within data processing limits. You can do some data logic for 777 kilobytes of data 60 times a second. Pretty much no problem. That should be okay. But as I hinted at earlier, this isn't a magic solution. There are two conditions to this for this to be our solution. The first is the same thing it's sort of been all along. Performance. You have to be able to rasterize in this format at interactive performance rates. So the tricks are going to be a little bit different than rasterizing your general purpose depth buffer, because now you have to respect the compressed format. Can that be done? That's a big question. And the other thing is what I said earlier. You have to have your depth buffer stay conservative in this compressed format. So it can never claim anything is closer to the camera than it actually is, or back to the issue of it saying some things are occluded that actually aren't, and that means things disappearing from view that should actually be visible, and that's just not good. So that's what it comes down to. If we can rasterize quickly in this masked format, and we can keep it all conservative, then this should be a completely viable solution for all the issues we've had with software rendering, or software occlusion culling so far. If this masked format meets these conditions, we should be able to do software occlusion culling at completely fair and practical performance rates for games, and get all the benefits of occlusion queries without any of the GPU sync issues. So really, it all hinges on, can we meet these two conditions? So, condition 1, performance. How can we rasterize quickly in this format? Because unfortunately, in the new format, a lot of the tricks that worked for the normal format won't work anymore. Well, for some of you viewers, for those of you who happen to watch my Minecraft channel on building redstone devices, you might actually already know the answer to this, because I created a triangle rasterizer on there using pretty much that exact format, and I had a really fast way to do it. And that's exactly what we can do here. So, for those of you who didn't watch the video, here's how it works. What you do is you start with your bit mask at all once, and you break your triangle down into edges. So what you'll do is, for a single edge, I will bit shift over enough zeros to meet the edge of the triangle. And that's just a single bit shift operation. I do one bit shift, boom, there you go. The edge is rasterized in the bit mask. And I'll need to do that for every edge, so yes, will require 3 bit masks total. So that's 1 bit shift, 2 bit shift, 3 bit shifts. Really fast. Bit shifts are a cheap operation. And once you have all the bit shifts done, well, all you have to do is AND the bit masks together, because anywhere it's 1 is considered inside the edge. If I AND together all the insides, the final result, well, the only thing that left is 1 is what's inside all 3 edges, aka inside the triangle. There you go. Simple as that. And it's a really fast way to rasterize in a bit masked format. So how fast is it exactly? Well, we need the 3 bit shifts. We need 3 subtracts, because we need to subtract the edge from wherever the start of the tile is to determine how much to shift over. We'll need 3 XORs, because we need to XOR the mask, potentially, basically optionally invert it. Because we're only going to basically shift one way, and we're going to invert the mask if the other side of the edge is considered inside. So that's the general idea. So we need XOR for that. And lastly, we also need a max, and that's a little bit more subtle, but like right here, if I subtract the edge from the bit mask, that's going to give me a negative distance. I don't want to do any negative bit shifts. I just want to shift over to 0. So in that case, yeah, that's what the max is for. I need to essentially clamp this so it's always greater than 0. And, of course, we need the 2 ANDs to AND all together. That's all the operations we need to do. And that'll completely rasterize 4 tiles, which might be a little confusing. You might think, hey Benny, why is this all it takes for 4 tiles? Well, keep in mind, for a single tile fits in a 32-bit integer. We can do all these operations on a 32-bit integer, no problem. Because, I mean, that's just how the CPU works. The CPU works on whole integers, so do all these operations on a single 32-bit integer, boom, whole tile rasterized. But CPU also has SIMD instructions, where they can do multiple integers at once. Just about every CPU nowadays has 128-bit SIMD, so we could do 4 integer operations at once. And in this case, since one integer is 1 bit mask, or, well, yeah, 1 tile, 4 integers, 4 tiles. We can do 4 tiles at once using simd. And the great thing about this is it easily extends to higher sim levels. If you have a really fancy processor with AVX 512 or a newer extension, you could do 512-bit simd and do 16 tiles at once. Or you could do the older AVX 256-bit, which isn't quite as widely supported as 128-bit, but a lot of CPUs have it nowadays. And then you can do 8 tiles at once. So this is great. This has excellent instruction level parallelism for that very reason. And in fact, just to give you an intuitive idea, never actually measure your performance like this. This is a terrible way to determine how fast an algorithm works. But just to give you an intuitive idea of how fast this works, for the 4 tile case, this is equivalent to rasterizing 18 pixels every single CPU cycle. That is ridiculous. That is stupid fast. So this is plenty fast enough for rasterizing the bitmask. Moral of the story, we can do it. The performance issue is solvable. It's great. It all works out perfectly fine. So, the final condition before everything is satisfied, before this becomes a truly viable technique, is the depth buffer must stay conservative. It can never say a triangle is closer to the camera than it actually is. And really the hardest part about this is just visualizing it. The logic is not that difficult, but it's a little weird to come up with a visual. So here's what I have. It's not perfect, so bear with me. But imagine this represents a tile. This is like the depth value of the tile, going from 0 to infinity. And somewhere in here we would represent what the bitmask itself looks like. I'll show you that in a moment. But yeah, this is a general idea. What we want to do is we want to take a triangle. Imagine this is like a 3D image with depth going into the screen. We're looking at the triangle like edge on. So this is the triangle. I know. The visual is tricky, but the logic should be okay. So let's say we want to add this in a conservative fashion, right? That's the whole idea. How do we add something conservatively? The logic is really straightforward. We'll generate the bitmask for the triangle, like we just talked about. And what we'll do is we'll OR that bitmask with whatever's already in the tile. In this case, there's nothing, so it just becomes the bitmask for the triangle, but if we had more, we'd OR them together. And the other thing we do is we set Z1 to the farthest point of the triangle. So that'll be right here. So altogether, that looks something like this. So Z1 is now the farthest point of the triangle, and as you can see, I've sort of illustrated the ones as this region. So this is where it's set to 1, this is where it's set to 0. Again, visual's weird, I know, but hopefully that makes sense. And yeah, this is a general idea. So as you can see, the depth in the depth buffer is always much, well, it's always farther away than the actual triangle itself. And something you have to keep in mind with this example is I know it looks like this isn't a great approximation because, hey, the triangle has this huge gap here. But something you have to keep in mind, this is a very contrived example. This triangle is very tiny. In reality, this would be like a 2-pixel sized triangle, so not that big of a deal. Most triangles would take up several tiles, and across several tiles, there's not going to be a huge discrepancy in depth for the most part. So for most cases, this should be an okay approximation for the triangle depth. So there you go. And that's really the general idea. So just to show you how it works when you add more than one, let's say I want to add another triangle. Now if I was adding it way up here, for just show you a brief alternative, if I was adding it way up here, then I could just add the bitmask and I wouldn't need to do anything to Z. Why? Well, very simply, this Z value is already farther away than the maximum value of the triangle, so we don't need to move it any farther. We can't move it closer because then it wouldn't be representing this triangle, but you get the idea. Again, this is a little bit of an edge case, quite literally in some sense, because usually you aren't going to have more than one triangle in the same tile. Usually triangles are going to be bigger than that. But if you have more than one, you get a little bit of this situation. And the depth is not going to be perfect. If I undo for a moment, there you go. So let's say it's in the original position. And the original position, it would be something like this. We'd have to move Z down to accommodate this triangle. And again, there's still a big gap. So that's something to keep in mind. No matter which way it goes, if you have two triangles, one of them is going to have a little bit more of a gap than necessary, and it's going to get a little bit weird. There is only so much you can do about that. That's one of the limitations of the format, but keep that in mind because there's another trick we're going to do in just a little bit to try and mitigate this a little bit. But again, for the most part, not going to be a huge deal because in reality, you're probably not going to see depth gradients quite this steep over just a couple pixels, assuming it's still the same object. But anyways, so hopefully you're seeing how the general idea works. So we set the depth, we set the bit mask, we set the Z1 so it's far enough for all the triangles. That's the general format. Really, the only time this gets weird is what if the entire line gets covered? What if the entire bit mask is set to 1? Then the bit mask is useless. It's not giving us any useful information at all. That's not any good. So, can we do something about that? Because as it turns out, we can. This is why we have the Z0, which you might have noticed we haven't used at all so far, other than just sort of being a placeholder there. What we can do here is, if the bit mask is all 1s, we reset the bit mask to 0 and set Z0 at what Z1 used to be. So, like this. There you go. It's representing the same depth information, but now what we could do is if I want to say draw triangle 1 again for some reason, I could get something similar to what I had before. I could sort of, well, wrong thing. I could get this depth layer where Z0 is now back down here instead, and it still captures everything. So that would be a more accurate depth thing for everything. Of course, it's not quite going to work. Well, actually, it is going to work. Never mind, this is going to work. But yeah. So it's a little... That's just a little bit of a thing to keep in mind. Once you've reset, you can add more triangles to this tile without hurting anything. And this is where you get the final trick to this, which is the heuristic. If it looks like a new mesh is being drawn, then you can reset the mask just like I described. And that way that can avoid some of those huge gaps if there's multiple triangles in one place. I mean, it looks like the new triangle is part of a new object as opposed to just, say, a vertex in the mesh, then it makes sense to reset the mask so that you can capture that extra depth information with the new bit mask. And that's really all there is to it. As you can see, it's still pretty simple, it's still pretty fast, and the main point is this can also stay conservative through everything. So that's it, viewers. We've met our two conditions. All the theory says this should be a fast and practical way to do occlusion culling. We should be able to do occlusion queries CPU side. They should run at reasonable performance, fast enough for a occlusion system in a real-time game without too much overhead, and it shouldn't have any of the GPU or CPU sync issues. We should have something awesome. But do we? So, it works awesome in theory, but how does it work in practice? And most importantly, what sort of performance could you expect in an actual game on actual consumer-level hardware? Find out next time! I hope you enjoyed, I hope you learned, and I will see you in the next video.